Hello, everyone. Welcome to the last session of our webinar on whitebark pine ecosystems and management. I'm Enzo Martelli, and today we're going to have two speakers who will going to be talking about the hydrologic roles of whitebark pine in the Greater Yellowstone ecosystems. There are David Thoma and Teo Rautu. Please, David and Teo, introduce yourself and connect your mic.
Okay, sure, yeah. My name is David Thoma. I'm an ecologist with the National Park Service Inventory and Monitoring Program in Bozeman, Montana. Primarily my work is in physical sciences, trying to link climate signals to the biology that we observe in our program. And we received a small grant from the Montana Water Science Center to study the effects of whitebark pine on the hydrology of the ecosystem. And Teo is our student who's working on this project. So, yep.
Hi everyone, I'm Teo and I'm a master's student at Montana State University, and for my project I will be using the water model that David will be talking about and using it to see how different whitebark pine stand characteristics affect snowpack and stream flow.
I guess we pre-recorded our presentation today because we have a busy week here in Bozeman with the Yellowstone Biennial Science Conference, where we're presenting other talks and posters. So I hope you can bear with us through the recording, and we'll be here live to answer questions and interact at the end.
We're going to talk about the hydrologic roles of whitebark pine in the Greater Yellowstone ecosystem. But first, I'd like to introduce my co-authors, Teo, who will be co-presenting with me in a few minutes, and Danielle Ulrich, Brian Smithers, and Aaron Shanahan. So 50 to 80% of Western water supply comes from snow, much of which falls on forests. So forests affect snow accumulation and melt, which affects the timing and volume of stream flows. So Western forests really are water reservoirs. And whitebark pine grows at the highest elevations where the snowfall is the greatest, so it might have a disproportionate effect on stream hydrology. So the Greater Yellowstone ecosystem is the headwaters for many important streams in the United States. The Yellowstone, Missouri, Snake, and Green all have their source in the ecosystem here. It's a high elevation ecosystem with lots of forested land and lots of snow. Just to give you an example of the importance of one of these rivers, the Colorado supplies water to over 30 million people. So the fate of forests in this ecosystem, if they have the effects on stream flow that we suspect they might have, are super important for the water supply for ecological and social reasons. So this map in the upper left shows the current drought monitor conditions in the Greater Yellowstone ecosystem, which suggests we're in extreme drought. The map on the upper right is just a zoomed in area for the rest of Montana. And these are news clippings that I grabbed last week from the web that talk about conditions in Montana and Idaho, where they're talking about water restrictions. But if we look at this colorful figure in the middle, we see the snow in different watersheds across the western US, where there's average or above average snow water and snow in the northern part of the western US, but much drier and lower water content in the snowpack in the southern part of the western US. Well, we hear about the wildfires in New Mexico daily now, so obviously it's clearly very dry and having significant impacts to forests there. But even when we have near average conditions like we do right now in the Missouri headwaters, that has 109% of average, we have to consider the record-breaking temperature that we've had recently. So last year we had the highest temperature recorded in Grand Teton National Park. So when we have these high temperatures and average snowpack, it's likely that some of that snow that might have been supplied to rivers and streams when it melts is likely going to go back to the atmosphere with these extreme temperatures. So layer onto that the effects of mountain pine beetle, blister rust, and wildfire that's both increasing in severity and area. And we have a really complicated situation for our forest, and subsequently probably some changes coming, if not already, to stream flow in the western U.S. So whitebark pine is a pioneer species. It's a food source and habitat for animals because of its nutritious seeds. And it has intrinsic cultural and spiritual value that I know all of you understand and appreciate, or you wouldn't be here. And it also has these hydrologic benefits, or so it's purported to, and that's the focus of our study. So what is the importance of whitebark pine to regional hydrology? Does it increase snow accumulation, stream flow volume, and does shading have all these benefits that it's supposed to have? And if all that is true, to what extent, and how might the fate of streams be linked to trees? So our research questions are fairly simple. We wonder, and have wondered for a long time since we witnessed the massive mortality event over the last 15 or so years in the ecosystem, what effect has all these dying trees had on stream flow volume, timing and magnitudes of flow, and the flow rates? And given that disease, drought, and fire will continue to shape these forests, how might those changes affect stream flow in the ecosystem? So central to our study is the use of a water balance model, and it's based on the premise that water is conserved. So water is mass, and mass can't be created or destroyed, so we should be able to track what comes in and what goes out. And water only has three options once it falls from the sky. It can go back up into the atmosphere via transpiration, evaporation, and sublimation, and most of that is water that's used by plants. It can go down and replenish water supply to groundwater aquifers and also become stream flow, and that's water that's used by fish, and if it makes its way to a wetland, that would of course be water used by frogs. So it has important ecological aspects there. Also, water can be stored temporarily as snow and soil moisture, and of course the soil moisture is what's potentially available for plants later in the growing season. So trees affect all of these processes, which is why we chose to use a model of hydrology that allows us to incorporate the effects of vegetation. On an annual basis, total precipitation falling on a watershed is equivalent to the sum of evapotranspiration, so water going back to the atmosphere, plus stream flow that leaves the watershed. So in the Greater Yellowstone Ecosystem each year, about 60% of precipitation becomes runoff and 40% is returned to the atmosphere. Those numbers are very coarse estimates, and it's really the subject of our studies to figure out what they really are. And trees play important roles in how precipitation is partitioned into these different components. And so that's why we're interested in the role of trees. Plus they're just really cool. Whitebark pine are amazing. It's an amazing species. Okay, so we have a pilot study that we established on the Buffalo Fork watershed of the Snake River, which contributes water to Jackson Lake. And what I've shown here is a trend in the normalized difference vegetation index. So that's a satellite-derived index of greenness that changes over time. And you can see here areas that are increasing in greenness. So those areas increased in production, vegetation production, or biomass over time. We see areas of forest disease where it's decreasing over time. And then we see this bright pink area that is the result of a wildfire from 2012. So there's a lot of complexity spatially in this watershed and a lot of change that's occurred over time. But fortunately, we have a USGS stream gauge at the bottom of this watershed that measures the cumulative effect of water flowing off this watershed. So we can use that to help us understand what the impacts of all these changes in vegetation might be having on stream flow. So our annual model allows us to consider some sort of basic relationships, like what is the relationship between annual precipitation and measured flow? In this case, it's got an R-squared of 0.69, so that's pretty good. But it turns out that the relationship between the maximum snow water equivalent in the snowpack when it reaches its maximum water content is a much better predictor of measured stream flow. And so this suggests why our interest is focused a lot on snow in these studies that Teo will talk about in a minute, but it also suggests why snow is so important to the western U.S. water supply. So in the Buffalo Fork watershed, we saw an increase in precipitation over time, and we also saw an increase in flow over time. And And that kind of makes sense. If the precip is increasing, we would expect flow to increase as well. But our real interest is not in the flow itself, but the proportion of precipitation that becomes stream flow. And that's what the figure on the bottom shows. It's the Q to P ratio, or flow to precipitation ratio. And we see that before disturbance, about 52% of precipitation became runoff. After the disturbances of forest disease and fire, about 64% of precipitation became runoff. So this represents a 12% increase in runoff efficiency. So for a given amount of precipitation, more runs off to streams after disturbance. However, if we want to answer more complicated questions about the maximum flow rates, minimum flow rates, and when they occur, we need a more complicated model, a more physically based model. So we have conceptually here a model that is tracking a lot of the different things that happen to water, and we can use this model to try to gain a better sense of what that seasonality looks like. We call that our daily model, and it's reasonably accurate, even off the shelf. We find that the relationship between measured and modeled flow has an R-squared value of 0.79. And it allows us, if we can calibrate and get this model to perform well, we can use it to estimate a lot of really important factors related to forest condition and stream flow. And these have real ecological importance related to fish spawning and base flows that may stress or not stress fish, depending on if they are below what the fish can tolerate. Because when the stream flows get really low, they can warm up more, and that causes a lot of oxygen stress for cold water fish. So in this case here, for this watershed, we see that after disturbance, the peak daily flow as a proportion of annual flow increased by about 1%. So at least it went in the direction we would expect. So we would expect bigger peak flows after disturbance. But the peak flows, the timing of peak flows occurred 5.4 days later. So that is not what we would expect after disturbance. But nevertheless, that's what we found. And it could just be because there was an increase in precipitation over time during this period shown in this graph here. And it just takes longer for greater or deeper snowpacks to melt. So one of the neat things that we can do with the hydrologic model is that we can decompose total flow into what we call quick flow and slow flow. Quick flow is the peak of runoff that's occurring about this time of year as the snow melt reaches its peak rate. Then after the snow melt completes, there's still water that's moving through the ground in subsurface layers to streams, and that's the slow flow component that sustains the cold water that fish need later in the summer. So in using this water balance and hydrologic model, we should be able to estimate some decomposition of these flows, which have really important ecological roles. So our challenge is to improve our model accuracy from an annual, monthly to a daily time scale so that we can estimate what these different ecological flows are. And that's really the subject of the rest of this talk, which Teo is going to present because it's the focus of her research.
Hi everyone, my name is Teo, and for my master's thesis, I will be using the water model that David talked about to assess how different whitebark pine stand characteristics affect snowpack and streamflow. I will be specifically looking at different canopy density classes, which consist of open stands, as defined by having 0 to 20% canopy cover, moderate stands, as defined by having 20 to 60% canopy cover, and closed stands, as defined by having 60 to 100% canopy cover. I will also be looking at different canopy damage extents, where healthy stands have low canopy damage and more live trees, and unhealthy stands have high canopy damage and more dead trees. Before I go into the details of how forest canopy affects hydrologic processes, I think it is worthwhile to see what other studies have found when looking at how changes in forest cover due to disturbances affect snowpack and streamflow. In one literature review, Varhola and others found that less forest cover increased snow accumulation, but also increased snowmelt due to less canopy cover shading snow. This led to an overall shorter snow retention period. As for how stream flow is affected by changes in forest cover, Sarah Goking and others looked at how stream flow was affected across 78 studies by either a non-stand replacing disturbance, such as a moderate bark beetle outbreak, or a stand replacing disturbance, such as a high severity fire or extensive clear-cut operation. For a non-stand replacing event, she found an equal distribution where water yield, or stream flow, either increased, decreased, or stayed the same. For a stand replacing event, she found that stream flow generally increased. There are a lot of other factors that can affect stream flow, such as the water holding capacity of soils and the precipitation amount. This leads to a large range of how much stream flow decreases or increases, ranging from -50% to over 200%. Because of many potential confounding factors, for my project, I will be collecting snow and stream field data across different canopy density and canopy damage stands to improve the water model and get better estimates on how stream flow may change as whitebark pine continues to decline. So how exactly does canopy density affect snowpack and stream flow? Starting here with an open stand, you can see this tree here that has this snowflake that represents its ability to intercept incoming snow. This cone shape structure represents its ability to shade snow. And then here, these white clouds represent different piles of snow accumulation. When looking at an open stand, you're generally going to have pretty high snow accumulation because, again, you have less trees that can intercept incoming snow. However, because more ground is exposed to solar radiation, you're going to have high rates of sublimation and a faster snowmelt rate. What exactly does this mean for stream flow? This blue hydrograph represents here the duration of stream flow for this open stand. Because of these processes, you're generally going to have an earlier peak flow due to the faster snowmelt, but you're going to have an increased water yield because of this higher snow accumulation. Due to the faster snowmelt, the seasonality of your stream is actually going to be shorter, where base flow is going to reach lower levels a lot sooner. What about when looking at a stand that becomes more dense and there are more live trees available? Generally speaking, you're going to have lower snow accumulation since you have more trees that are intercepting incoming snow. But this shading factor is going to be really critical, where trees are going to shade snow and protect snowpack, increasing snow retention. This shade is also going to slow the snowmelt rate. And so what does this mean for stream flow? This closed stand refers here to this green hydrograph, where because of shading and slower snowmelt rates, you're going to have later peak flows. There's also going to be lower water yields due to this lower accumulation, but the seasonality of stream flow is going to be longer, where you're going to have your base flow be prolonged longer than an open stand. So how exactly does canopy damage or general forest health affect snowpack and stream flow? This diagram here to the left represents a generally healthy forest stand with low canopy damage, where you have a couple of dead trees. These smaller snowflakes right here show that when compared to a live tree, the canopy interception of a snag is lower, in addition to its shading factor being smaller when compared to a healthy tree. When looking at the inputs and outputs of snow, you're generally going to have lower snow accumulation in a healthy stand because you have more live trees that can intercept incoming snow. Additionally, you'll have more extensive shading since these healthier trees can shade out the snow and protect it and increase snow duration, leading to overall slower snowmelt rates. What exactly does this mean for stream flow? For a healthy stand with low canopy damage, it's going to correspond to this green hydrograph, where because of increased snow retention, you're going to have later peak flows. You're going to have lower water yields since you have lower snow accumulation, but you're also going to have longer stream flow seasonality, where because of the protected snowpack, your base flow is going to be more drawn out. What about for a stand that has higher canopy damage and more dead trees? When looking at the different snowpack processes, you're going to have a generally higher snow accumulation since there are less live trees that could intercept incoming snow. Since more ground is going to be exposed to solar radiation, you're going to have higher rates of sublimation and also just have faster snowmelt rates. What does this mean for stream flow? Well, this high canopy damage stand is going to correspond to this blue hydrograph, where because of the increase in snowmelt rate, your peak flow is going to happen earlier. You're going to have a higher water yield due to more snow accumulating on the ground, but you're also going to have a shorter stream flow seasonality, where your base flow here is going to dramatically reach low levels a lot earlier. So to better understand how different whitebark pine stand characteristics affect snowpack and stream flow, I have established field sites across different canopy densities and canopy damage classes. I'll be collecting snow data in these different stands to see how much snow accumulates. In the springtime, I'll do repeated sampling to see how quickly snow melts across these different classes. I've also established 2 stream gauges, one that drains a healthy whitebark pine stand and one that drains an unhealthy whitebark pine stand, to see how tree mortality influences stream flow seasonality. Once I've collected all of my field data, I will then be incorporating it into the water model to better improve its accuracy in predicting changes in stream flow. One of the key components of the water model that David touched upon is its ability to use NDVI. NDVI is a metric that is commonly associated with vegetation cover and ranges from values of 0 to 1. You can see here in the picture to the right where a green healthy plant generally has a higher NDVI value, whereas an unhealthier dying plant may have a pretty low NDVI value. Using NDVI can give us better estimates of evapotranspiration, as well as winter and summer interception rates and melt rates. So for example, for this green plant that has a higher NDVI value, we would expect to have higher evapotranspiration, higher interception rates, and a lower melt rate since it's likely shading out more snow. We can use NDVI to track general plant health over time. So for example, right here, for this area that was afflicted by a wildfire, you'll notice that in 2012, there was this dramatic drop in NDVI representing when the fire burned that general forest stand. Down here, you might have a less severe mortality event where a forest stand might be afflicted by some kind of disease or is drought stress, and you'll notice this slight decrease in NDVI. Up here, where you have potentially a healthier forest stand, you'll notice this slight increase in NDVI, suggesting forest growth. By including NDVI data to better estimate evapotranspiration and my field data to better estimate canopy interception and snowmelt rate across different whitebark pine stands, we hope to improve this water model as much as we can. In other words, we hope to really increase this R-squared value, where there's a really tight correlation between the modeled runoff and measured stream flow from different stream gauges. It's really important to have an accurate water model because this will become really useful for modeling future climate and disturbance impacts on stream flow, where we'll expect to see different changes in canopy cover. Another benefit of this water model is that it is an empirical lumped model, meaning it is a relatively simple model that can be applied to other watersheds where I might not have or I might not get field data. We also hope to use this model to other stands of different forest types throughout the Greater Yellowstone ecosystem. Even though I am in the midst of collecting my field data, I wanted to share some preliminary findings that I've been able to get through some various spatial analyses. So for one of my preliminary analyses, I was interested in seeing how snow accumulation compared across different whitebark pine stand characteristics, specifically across the three different canopy density classes, open, moderate, and closed, but also the 4 different canopy damage classes where you have low canopy damage, medium, high, and very high. The data I used was April 1st snow water equivalent, which is the same as how much liquid water is stored in the snow. The reason I used April 1st is because that date generally represents peak snow accumulation, since it's shortly after all of the significant precipitation has occurred in the wintertime, but it's shortly before all of these snowmelt processes start to come into effect. The map here on the right shows the whitebark pine dominated stands in teal that I used for this analysis, whereas the orange represents the entire whitebark pine distribution. So when first looking within each whitebark pine stand category, you'll notice that SWE, or snow water equivalent, generally increases with less canopy cover. You can see this here with this healthy whitebark pine stand category where this dark bar represents the closed stand, this middle bar represents moderate, and then this top bar represents an open stand, and SWE increasing going from closed to open. This is what we would expect to see, since in open stands, you have less trees available that catch incoming snow with their branches and prevent snow from accumulating on the ground. When looking at the total healthy whitebark pine stand SWE and comparing it to the SWE in unhealthy whitebark pine stand, you'll notice that there is higher SWE in the unhealthy versus the healthy. This is again what we would expect to see, since in these unhealthy stands, you have less green leaves that can intercept incoming snow. These findings stress the importance of canopy interception and how it is a key characteristic of whitebark pine stands that determines snow accumulation. So how does SWE compare across the different canopy damage classes? Well, when looking within each damage class, you'll notice that SWE increases with less canopy cover. This is what we would expect to find, since in these open stands, you have less trees available to intercept incoming snow. In the very high damage class, you don't really see much variation across these different canopy density classes. This suggests that the dead branches in this very high damage class are just not very efficient at canopy interception, and so density of these branches just are not a big contributing factor for snow accumulation. When looking at SWE across the 4 damage extents, you'll notice that for the closed canopy cover stand, there's a general increase. This is again what we would expect to find, since as these closed stands are losing their green leaves, their canopy interception is decreasing. Interestingly enough, though, we found the opposite trend for the open stands, where as the open stands were losing more of their green leaves, SWE actually decreased. This suggests that sublimation might be a contributing factor and actually override the snow accumulation processes in these open stands. After looking at how different whitebark pine stand characteristics affect snow accumulation, I was also interested in seeing how whitebark pine mortality affects streamflow. In 2009, the Greater Yellowstone Coordinating Committee created these maps to show the extent of the mountain pine beetle outbreak throughout the GYE. I decided to focus in on the upper Wind River Basin and compare streamflow before the outbreak, during the outbreak, and post-outbreak. This map here shows the USGS stream gauge that drained these orange clumps, which represent the whitebark pine stands that were afflicted by the bark beetle outbreak. My data for the pre-outbreak was limited to just 2001 to 2003 due to data availability, but I was able to get extensive data for during the outbreak and post-outbreak. So just to look at the raw data first, we have the daily mean stream flow plotted from the pre-outbreak to the outbreak and to the post-outbreak. Precipitation was also plotted here above. You'll immediately notice that the peak flows start to increase during the post-outbreak period. To see if this was more so because precipitation was increasing during this time period, I calculated runoff ratios, and you'll see that these ratios are increasing, meaning that a higher proportion of precipitation is resulting into runoff. This leads us to the conclusion that whitebark pine in this scenario is indeed leading to an overall increase in stream flow. So from our preliminary analyses, we can expect that whitebark pine forests increase snow retention, slow snowmelt, and prolong streamflow seasonality by supporting longer summer base flows. This will be important to continuously monitor as whitebark pine populations are expected to keep declining and have its range contract in the near future. Another avenue for future research is how other tree species may come into effect. We're already seeing dead whitebark pine stands being overtaken by other species, such as subalpine fir. This raises the question of how these species interactions may impact future water availability as whitebark pine continue to decline. With that, we'd like to thank our collaborators and sponsors, the Montana Water Center, Sitka, University of Wyoming, the U.S. Forest Service, and the National Park Service. And now we are happy to take any questions.
All right. Thanks so much for your presentation. It was really insightful. Okay, so before we start with our Q&A session, we have two ways of receiving your questions from the public. One is either leaving your questions in the chatting box, or the other one is raising your hand if you want to unmute your microphone and talk directly to the speakers. So let's start with the question. So in the chat box, Eric Geisler says, how might wind affect SWE in open stands of unhealthy trees?
Yeah, good question, Eric. So it's been found that in a stand where you have more dead trees, it doesn't provide as much wind shelter. And so that rate of sublimation, because of more wind kind of taking the snow up to the ground and enhancing that process of melting back into the atmosphere, we might expect to see SWE be lower in those open stands of unhealthy trees, but it can just really depend on like how prevalent that wind factor is. We could see that happening more like maybe on top of ridges where you get more exposure and it is more windy, but maybe like at a lower elevation, that wind might not be as big of a factor.
Thank you. There's another question here that says, when you establish your pods in both basins, did you find any strong differences in terms of the assemblages of the dominant tree species?
So for my plots, I'm specifically looking at whitebark pine dominated stands where whitebark pine is the dominant species, but in other stands nearby, I am seeing, for example, at Beehive Basin in Big Sky, where subalpine fir is really regenerating in the understory and taking over those dead whitebark pine trees or any other potentially live whitebark pine. So as I collect more field data over the summer to really look at species composition, I will be taking note what other kinds of species are there.
Thanks so much. There's another question from Ben Sobolski that says, did the PAP stand have clumps and gaps of live and dead trees, or was the canopy more evenly distributed, and how would each affect P and Q?
So I haven't gotten a chance to do a whole lot of field work yet. I'll be better or able to better answer that question after the summertime. But in terms of what stands I have looked at, I would say that there was kind of like any live trees would be more in an open stand that maybe didn't have other competitors nearby. And I would say as for in terms of dead trees, kind of just at least one stand that I looked at, it was spaced in the clumps where depending like on the topography, you might have some more clear clumping, but it was a little more evenly distributed in those stands. And then I guess the other question was how would each affect precipitation and discharge? I guess in terms of just having fewer live trees, I would expect that there would be more trees that evapotranspire, so we would see less streamflow or less discharge. But with dead trees, since they're just not going to evapotranspire at all, I would expect that streamflow would then be higher for those stands.
Thanks so much. A personal question. At the beginning of the presentation, you mentioned that the soil properties would be another factor to consider in terms of snowmelt runoff and other like snowmelt behavior, right? So are you considering these factors in your sampling? Say the type of soil, textures, or understory cover.
Yeah, that's a great point. In terms of, and if you want to talk more about this for the water model, there is a soil moisture parameter in the model that does account for that. In terms of my field work, I haven't considered like taking soil pits or soil moisture measurements, but I know that there's also some like GIS layers that have mapped out and give you a sense of like what the water holding capacity might be for those soils. Did you want to say more about for soil moisture?
Yeah, one of the challenges is even if we did have soil data in some of these places, and most of them we don't. A lot of them are wilderness areas where soil surveys haven't been conducted. And even if we did, it's hard to know what volume of soil tree roots explore, because they're pretty crafty. They can go down deep cracks, and they can use water stored in rock if it's the right kind of parent material. So what we found is oftentimes we have to calibrate the model to the local conditions against something like NDVI. So in that case, when we do that, we find that oftentimes the water holding capacity of a site might be more than twice what our estimates of soil water holding capacity are. So that's a good question, and it's a tricky thing to address, but I think through calibration, we might be able to get closer at it than we can even by trying to estimate it using field sampling techniques in some cases.
That's a great response. Thanks so much. And just to add a little bit something to what you were just saying, are you considering calibrating the model for the difference in slopes?
Yeah, I can answer that one. Yes, we do have a heat load factor built in as a modification of potential evapotranspiration that takes into consideration the slope aspect. So whether it's north or south, whatever 360-degree compass reading it is, and also how steep it is, whether it's a relatively shallow or a steep slope. And so like steep south-facing slopes will dry out much faster in this model and that is consistent with what we see in NDVI when we look at the signals from north or south facing aspects.
Thanks so much. There's another question from Diana Tombach that says, one pioneering study of this was field farmers on Mount Whitebark. He initiated the idea that Whitebark pine stands were important in regulating downstream flows, and he looked at southwest east. Any thoughts about how he approached this? I mean, southerly, sorry.
From reading his description, I didn't see any actual quantitative data on this, but I know that he kind of gave this more qualitative description of how this whitebark pine might be able to increase snowpack retention and that way regulate downstream flows. But I personally don't know more about how he came to those conclusions with actual numbers.
All right, so it seems that until now, those are all our questions. So now we will leave around 5 minutes to in which Kara Nelson needs to say some words. So give me just 1 minute.
I think there's just one more question in the chat from Sarah Goking. She's asking, how do you think, how do you think the effect of whitebark pine mortality and its effects on snow retention might affect growing season soil moisture and thus possible regeneration, resilience of surviving trees? I guess my take on it is that by having more dead trees or dead whitebark pine trees, you'll have more water available for understory regeneration. So in a way, it could potentially enhance or have more soil moisture available for other trees that are growing the understory. But at the same time, because with more dead whitebark pine trees, they're going to not shade the snow as well. Snow is going to melt a lot quicker and your snow retention is going to be shorter. So in that sense, you could see it where maybe then the duration for higher soil moisture might be shorter, and maybe then trees or the understory trees might not have water available for as long of a period. But yeah, it's a great question. I'm hoping to get a better sense from my field work. I don't know if you want to add on to that.
I guess the thing that strikes me about that question is that these are really complicated processes, and that's one of the reasons why we're using a water balance model to try to understand some of these really complicated interactions, and everything from water holding capacity to slope aspect to the vegetation type, the rate of snowfall and its melt rate, all affect water in the soil later in the year that might be taken advantage of by regenerating seedling or germinating seedlings and those that are trying to become established. So yeah, this is all of these are complicated questions with lots of interactive factors. I think the modeling approach, even as simple as the one that we're using, I think can help address some of these questions. So thanks for that question. I guess to any of you who have thoughts on these discussion points that would want to follow up with this, we welcome conversations, because as far as I know, we're the first ones to try something like this. And I know that there are more complicated approaches and models that can be implemented, but at the scale we're working at with the limitation of the data that we need to run the model, we're hoping that it is sort of a nice match between data availability and efficiency of the information that can be generated.
All right, thanks so much, David and Teo. Let's pass it now to Kara.
Take a minute, load up my screen here. Oops, that's not the right. Let's see. Stop share. Sorry, everyone, trying to get my share screen correct here. Are you seeing the PowerPoint?
Yeah, we can see it.
Okay, great. There we go. Well, this brings us to the end of our first installment of the Whitebark Pine Ecosystem Foundation's webinar series. Danielle Ulrich and I have been the organizers of the series, or really the coordinators of the series for the year. And I'm so pleased with how it's turned out. I want to take a minute to thank all of the spring 2020 speakers for sharing their time and experience with us, from Taza Shamming and Lorinda Bullington, who did the first two presentations, and then Erin Shanahan and Chris Ray, and then to David and Teo today. We really appreciate your being willing to join us and help launch the series. And you will be receiving foundation hats in the mail from us shortly. They're newly created hats. So this is a new product for the foundation, recognizing, it's a small thank you to recognize your time. I also want to thank our student organizers of the series. We had a team of 4 students who pulled together all the speakers, the webinar platform. I want to especially thank Vlad for handling all the communications, the registrations, etc. We had 2 organizers from University of Montana, Vlad and Enzo, and then we had 2 organizers from Montana State University, Sean and Chloe. And I've listed their research areas of their theses and dissertations on this slide, but they are also going to be the subject this week of a research spotlight through the foundation social media channels. And you guys, we have hats for you, and we also have annual membership in the foundation. Most importantly is to thank all of you for participating. We have 285 registrants, and we've had over around 100 people participating in each of these monthly events. The idea is to share knowledge about both the ecology and management of whitebark pine, but also to foster community and have a chance to understand who is working in whitebark pine and how we can work better together to increase understanding and foster better conservation. The series is taking a break for the summer field season. We'll be back in the fall. We'll be running September through May. Again, the 3rd Tuesdays of the month at the same time, noon time, Mountain Time. And it's the same registration link, so you don't need to re-register, but please do share the opportunity with your networks. In addition, I hope those of you who are not members, we've sparked your interest to take a look at the website. I've listed the URL here. On the website, you can become a member and you can learn more about the work of the foundation. I've also listed my email. If you're interested in presenting in the series next year, please drop me a line, a note. You could also suggest a topic, even if you're not interested in presenting. Also, we aim to have students again organize the series for next year. So if you're a student and you're interested in joining the organizing team, the students will be meeting through the summer to put together the calendar for next year, and we should have that calendar out and available for the full set of talks in the series next year. Should be available in August. So students, let me know if you're interested in joining. We'd love to have you on the team. And so with that, I think that's a wrap for the series. I hope everyone has a great summer, and hopefully we'll see you back here next fall.
Thank you.
Thank you guys for your time.